I would like to thank the organizers for inviting me to this talk here and the opportunity to speak to you, especially because or we as a group are sort of outsiders to this community. So many of you I've met here for the first time. I have to say it's been incredibly exciting and instructive. I've learned a lot, and I just hope that I can give something back in sort of maybe stimulating some collaboration, some discussions in talking about Rydberg atoms and optical lattices. Now, we've heard a little bit about Rydbergs and optical lattices just now from Georg Raithel, and they've been mentioned on and off over the last 2 days. And I think what I really want to do is, I don't want to give you much motivation because this has already been covered in Hans-Peter Büchler's talk. Charles Adams has mentioned lattices as a way to sort of pre-correlate the spatial distribution function of atoms in order to better control the interactions between the Rydberg states. So I think I'll skip over this very quickly. Now, what I really want to talk about today is what we can do with optical lattices, because obviously we are an optical lattice group, right? So this Rydberg atoms in optical lattices you can approach from 2 ways. You can either have Rydberg atoms already and then just add an optical lattice, which I can tell you is easy. Or you can, as we do, have optical lattices and know what to do with them, but then you need the Rydberg atoms, and that's difficult, at least in the experiment, as we've learned. And I'll acknowledge towards the end of my talk the people who've been a tremendous help in taking that step. So I will start by telling you a little bit about the techniques, because many of you might not be familiar with how optical lattices are actually produced in the laboratory. Then I'll tell you how we can control the matter waves in these optical lattices, the BECs that we create. And also talk a little bit about diagnostic tools, because I think that's what's going to be interesting and important in the first steps in combining Rydberg atoms with optical lattices. Then obviously, because otherwise I wouldn't have an excuse for being here, I will show you about our Rydberg setup, which is only now beginning to actually function. So I'll talk a little bit about the ion detection, calibration of our laser, so that's going to be rather technical, and I'll do this very quickly. The field control, these are all problems of a sort of experimental nature, but might be interesting in terms of then knowing what to do once we have the Rydbergs and lattices. And we actually have some first results, and those are going to be rather raw data because they came in yesterday, and so I just patched them into my talk. You know, you can always claim that this is the way it happens, but it is actually, so I'm very glad that this worked out. I had some sort of minus first order results from last week, but they weren't very nice, so I'm glad that I got some nicer ones. And then I'll conclude and give you a bit of an outlook. So just a very brief sketch of how we get to the point where we're at. So we start with rubidium atoms. We laser cool them inside a magneto-optical trap. Then we transfer them into initially a magnetic trap and then a dipole trap and perform evaporative cooling. So we just lower the depth of this conservative trap, and the atoms cool, and then we form a BEC of rubidium atoms, about 10 to the 5 of them. The optical lattice is then the easy part, actually. We just add laser beams, I'll show you in a minute how, that create an interference pattern at the position of the atoms. So you get this sort of egg carton-like distribution of atoms in 1, 2, or 3 dimensions as you choose. So the optical lattices, as I said, are simply counterpropagating linearly polarized laser beams that form a standing wave interference pattern with a spacing of half the laser wavelength. And already at this point I can tell you that there are techniques which allow us to realize different lattice spacings, which might of course be important if you want to change the spatial dimensions of these crystals. So all you have to do is have the 2 laser beams propagate at an angle with respect to each other, and that means that the effective lattice spacing that you get, the standing wave pattern, is then lambda over twice sine half the angle between those beams. And if you put in numbers, realistic numbers for the lab, this means that we can actually vary this lattice spacing between half a micron, which is roughly half the wavelength of our laser, and actually several microns. So we've got a lot of flexibility in that respect. What we can also do with these optical lattices, we can move or accelerate them. So we can actually create forces on the atoms inside these optical lattices in the rest frame of the lattice. So what we do in order to move or to accelerate the lattice is we simply add a small frequency difference between those two counter-propagating beams. And if the frequency difference is constant, then this just means that your standing wave pattern moves at a constant speed. If you interpret linearly, it means it moves at an increasing speed, and so you've got an accelerating potential, or in the rest of the lattice, you've got a force acting on the atoms. Now, the way we look then at what has happened to the atoms, either in an accelerated or in a stationary lattice, is we just switch off the lattice and all other confining fields, and we let this macroscopic wave function, so the different parts of it originating from different lattice wells, interfere with each other, and we get a sort of multiple slit interference pattern, just as you would with coherent light propagating through an n-slit pattern. And so this is just a schematic of this. In the lab, it looks like that. This is just a resonant flash shown onto the atoms, and you see the shadow that is cast by the atoms, and you see this three-peaked interference pattern. In this case, if you had accelerated the lattice beforehand, then you would actually transfer momentum, or in this time of flight picture, you would see sort of the interference patterns shifted out to one side. And in the lab, this looks like this. And I'll come back to these patterns later because they'll be important in defining the coherence properties of our system, because obviously you only see these nice interference peaks if your initial matter wave was coherent, so if you had long-range coherence over different lattice wells. Otherwise, you just see a washed-out blob, just as in the case of coherent or incoherent light. Now, just a blast from the past to tell you how we got into this business. So this is a very old publication of ours where we looked at what happened when you actually accelerated the lattice in one direction. And of course, what you expect to see, as in solid state, you expect to see Bloch oscillations when you put on a constant acceleration. And this is what you see here. This is the velocity of the atoms in the rest frame of the lattice. So you see these nice oscillations, and this is a band structure calculation. So, you know, this way we figured out that we could actually control the wave function in this way. Another topic that we approached very recently is Landau-Zener tunneling at the edge of the Brillouin zone. Okay, so if this is the band structure at the edge of the Brillouin zone, we know we have Landau-Zener tunneling, and we know the expressions for the probability after performing this Landau-Zener tunneling for atoms to be in the ground or in the excited state. But we were interested in actually looking at the time evolution. Okay, so at each point during this crossing, what happened to these two coefficients in the ground and the excited state. And the reason why I'm telling you this is just to show you that we have a very good control over our lattice. We can, for example, track such a single Landau-Zener crossing in a time-resolved way, and this is the result. So you can see here, this is as a function of the position inside the Brillouin zone, as a function of quasi-momentum, the probability for atoms remaining in the lowest band of the lattice, and you can see that you've got this nice sort of sigmoid-shaped transition here. So this is measured in the adiabatic basis, which I just showed you. We can also measure in the diabatic basis of the free particle wave functions, and then you get what is called Stokes oscillations. So all this is just to show you that we understand very well what's happening to the atoms in these optical lattices, and that we can control them very well. Another diagnostic tool that we have developed, which is actually quite obvious, is to study tunneling between these wells. So if you've got Bose-Einstein condensate that you confine initially in a harmonic trap to keep it A from falling down and B from expanding, and you want to know how fast atoms tunnel between these potential wells, because obviously they can tunnel through them quantum mechanically, then in this configuration you don't really have access to that because you can't put labels on the individual atoms, so you don't know whether this atom goes there or remains in the other well. So what we can do, though, is we can switch off the confining potential in this direction and just look at how fast the condensate expands through quantum tunneling. And this was an experiment in which we varied the depth of the lattice, and obviously this tunneling matrix element goes exponentially with the lattice depth. And you can see that this agrees well with the theoretical calculation. So we also have this as a diagnostic tool for looking at dynamics inside the optical lattice. Another thing we got interested in very recently was dynamical localization. So just very briefly, for those of you who know it, it's obvious. For the rest, you can ask me later. We can actually now look at expansion inside this optical lattice when we very strongly drive the lattice. So we just shake it back and forth, which in the rest frame of the lattice means that we apply a sinusoidally varying force to the BC, and this from solid state is known as dynamic localization. And here you see an expansion as a function of time of the condensate in just a stationary lattice. So you got an almost linear expansion as a function of time. And it turns out that if you choose the frequency and the amplitude of this driving intelligently, and well, this just means you work out theoretically what it should be. So for some combination, you actually find that you get no expansion at all. For intermediate values, and this is now a real-life sort of shot in situ inside the optical lattice, not after a time of flight, of an expanded wave function after about 100 milliseconds, and these dashed lines are the original width of the condensate. You can see that when we don't drive the lattice, we just get expansion through quantum tunneling. Then when we start driving the lattice, tunneling is reduced up to the point where it's completely suppressed. So here this initial wave packet is completely frozen in its position. And then when we shake the lattice harder, tunneling actually resumes, which comes as no surprise. I mean, it all comes out of the maths if you do it correctly, but it just shows you a nice additional way of controlling the wave function. This is another way of plotting this. So here you can then work out in a sort of effective tunneling matrix element if you take into account the suppression due to shaking. And you see this follows a sort of a Bessel curve. Actually, the modulus of a Bessel curve, because in this experiment we are not sensitive to the sign of the tunneling matrix element, which actually changes sign here at the 0. I'll show you in a minute that we have access to this information in a different experiment. And all this is done in a sort of high frequency approximation, so this shaking motion has to be a lot faster than the tunneling time in order for this to work. So this is like a high frequency version of dynamic localization. Another observable that we have in these experiments, as I showed you before, is this time of flight interference pattern, which tells us something about the coherence of the wave function. And in this experiment particularly, we're interested in seeing whether our wave function actually stays coherent when we shake very strongly, or whether this sort of breaking down of the tunneling is just something that catastrophically happens, everything becomes incoherent, and hence you don't tunnel anymore. And the way we do this is we look at the visibility of this pattern, which just simply tells you how well these peaks are visible, just as in spectroscopy. And we do that as a function of time. And here you can see that the coherence times here on the order of hundreds of milliseconds. So our system stays coherent for a very long time. And over a very large range of amplitudes, this is the sort of reduced amplitude of the driving. And you can see here something funny happens, though, around 2.4, which, as we saw before, is the point where tunneling is completely suppressed. And here the coherence time actually drops by a factor of about 100. Okay, and this is not very surprising when you take into account that not only do the atoms tunnel, but they also interact with each other. Okay, so they collide. And when tunneling between adjacent wells is completely suppressed, the only phase evolution is now local. And in each lattice well, there is a varying number of atoms, so they all accumulate slightly different phases and very quickly go out of phase with each other on a timescale of a few milliseconds. Okay? So all this, again, is just to show you that we have very, very powerful tools to track the coherence, to investigate the coherence of the system. And this might be useful then also for experiments where the coherence might be compromised or altered due to interactions between Rydberg atoms in the lattice. Just as an aside, as I told you before, on the right of this 0 of the Bessel function, around 2.4 of this driving parameter, the effective tunneling matrix element actually becomes negative, and this is reflected in the time of flight pictures. So you now get an interference pattern that looks, for those of you who are familiar with these pictures, like something that's at the edge of the Briand zone. Okay, so you've got a staggered state of the matter wave function. Okay, another useful tool, I'm sure, that will come in very handy when extending this to having Rydberg atoms in the optical lattice is the Mott insulator transition. So just a brief recap. Now, if we go to a 3D configuration of 3 orthogonal optical lattices, we get this sort of cubic structure, okay, this 3-dimensional crystal. And now it turns out that when you reduce tunneling between those adjacent sides, then the onset interaction that I mentioned a minute before becomes dominant, and you actually go into a regime where number fluctuations on site are completely suppressed and phase fluctuations basically diverge. And the way you can see this is by looking again at the interference pattern. So this is some data from about a year ago, where we have a nice interference pattern for a reasonably shallow lattice, about 10 recall energies. Then we ramp it up. We create this Mott insulating state where we've got a fixed number of atoms in each lattice site. So ideally, probably for experiments with Rydberg atoms, just one atom per lattice site. Okay, so then we could actually realize the theoretical proposals by Hans-Peter and others. And we can drive that back adiabatically to a superfluid state where we've got phase coherence again, and this interference pattern reappears. Okay, again, another aside, but which I thought was quite cute. So this is a setup for creating such 3D lattices in the lab. We just have laser beams coming out of fiber couplers. They're retroreflected by mirrors, and at the intersection form this crystal. Now, as I said before, by shaking the lattice back and forth, we can actually reduce tunneling. So we just investigated another way for creating the Mott insulator transition by very strongly shaking this lattice in all three directions, simply by putting the mirrors on piezoelectric transducers and actually shaking the lattice in real space. And what we found that in this case also we could suppress the tunneling sufficiently so that we realized the Mott insulator transition. So here we didn't change the depth of the lattice, which reduces obviously the tunneling rate and also increases the onset interaction because the wells become deeper. But we just started shaking the lattice, reduced the effective tunneling matrix element, and hence induced this quantum phase transition. So another element of control which always comes in handy, I guess, when it comes to implementing all the various schemes that are floating around. Now, as promised, I'm now coming to the Rydberg part of our experiment. So this is the entire experiment, and obviously I'm not going to tell you what all these things are, except to say that everything happens in here in this little glass cell of a few centimeters across. So we start with a 2D Mott, which is back here to collect atoms. We then have a 3D Mott in this region here. We first have a magnetic trap. Here are the coils, and then a dipole trap, which you can't see, just the laser beam going in here. And we condense about 10 to the 5 rubidium atoms, and we then add an optical lattice at 852 nanometers with beam widths of about 100 microns, and we can realize up to 50 recoil energies of lattice depth. Now, some peculiarities of our system: we have a glass cell, and since this was designed primarily as a BC apparatus, and the Rydberg atoms were only sort of an afterthought that we had when we designed it many, many years ago. We never thought, actually, or never thought that we would come to the point of actually using it, but there you go. So we put in a channeltron into our system and a grid in order to define some electric field, but we sort of forgot to put in some other electric field plates to actually have a clean electric field in this region here, so we had to put them outside, which creates some problems, and obviously the fact that we have a glass cell here in close proximity also creates problems with charging effects. So all the electric pulses that we apply in order to field ionize the Rydbergs created in this area and to accelerate them towards the channeltron have to be very, very short. If they're longer than a few milliseconds, then everything charges up and we have to stop for a few hours. So we took very long coffee breaks initially before we realized this. Well, actually the coffee breaks weren't very relaxing because we thought we'd broken something. But anyway, so we learned the hard way, but it's something we'll never get wrong again. So this is just a time of flight signal. You've seen many of those before. So most of the experiments I'll show you here are just done in a magneto-optical trap, which we used in order to calibrate our system and to learn about Rydberg atoms. A slight difference compared to many other schemes that we've seen here. Our first step in the two-step creation of Rydbergs is actually on a blue transition to the 6p 3/2 state. And then the second step is a red laser. So that's just something we decided to do early on, which may have disadvantages and advantages, but for the time being, that's just the way it is. Some very preliminary experiments which we used to just check that we were able to stabilize our lasers, and we use cavities to lock them to each other. That's also something we had to learn because you never have to do that when dealing with BCs. So here is just a spectrum of ionization of the ground state via this intermediate state. So we go directly to the continuum and we resolve this structure of the intermediate state, the different F levels. And this was basically just to see whether our channeltron was still working, because it had been sitting in there for a couple of years and somebody had told us that these things don't get better with time. And so we were quite curious to see whether we would actually detect any ions. Well, this is actually the Mott loss, but we got the same spectra with the channeltron just to compare them to each other. And this worked out fine, so we're quite happy. Having satisfied ourselves that our channeltron was working, we then tried to create Rydberg atoms and field ionize them. So these are the results. So we've got here is n equals 50, the d3 halves and d5 half states, the 59, the 81. We just played around with a number of different states just to see what our limits were in tuning our laser, for example, and also in terms of the width that we could realize. So all this worked out pretty well. We then went on to do a coherent two-photon excitation. So we detuned the intermediate state by some amount delta and excited, this is the 50D state. And here you can see the black line is with zero detuning. So, with 100 megahertz detuning. So you see this coherent two-photon transition. This is all heavily saturated, but we just wanted to show without changing the parameters that this works. And so you here still populate the intermediate state, and as you detune further and further, you start seeing this green line here with virtually no contribution here at zero detuning, and then a completely coherent excitation of the Rydberg state, the 50D in this case. Another thing we had to do, obviously, we had to measure the outer town splitting to check what the Rabi frequency was on the first step of our transition. So here is a spectrum for increasing power of the first step, so the blue laser, and you can see the splitting here increases, and we can deduce that we've got something like 50 megahertz of Rabi frequency on the first transition. So the splitting here is then fit by the theoretical curve, which works out reasonably well. Something I mentioned earlier on, the electric field was actually a major concern to us. So we did some Stark spectroscopy of a high-lying Rydberg state, and so the electric field here was calibrated by just comparing it to the Stark map. And we satisfied ourselves that the residual electric field, when we weren't making any mistakes, such as leaving on the field beds for too long, was actually less than 10 millivolts per centimeter. And we can't pin it down better at the moment, but we believe that this is good enough for many of the things we have in mind immediately, and may have to be improved upon for more sophisticated experiments. This is just an example. Now, as I said, everything I've shown you before was in the magneto-optical trap of ionization of a Bose-Einstein condensate. I'm not going to go into, of Rydberg creation in a Bose-Einstein condensate. I'm not going to go into any details except to say that here around the resonance where we expect to see a lot of Rydberg atoms, this is heavily suppressed, which is almost certainly a sign of the dipole blockade. But Thielemann Pfau is the expert on that, so I'm not going to talk very much about it. There is a mechanical effect on the BC, obviously, when due to excitation of the intermediate step simply by photon scattering. So if you don't excite completely coherently the Rydberg state, then you get some scattering of atoms. And you can actually see that by the BC A heating up and B being really kicked into one direction. And you can see here these are the three F states of the intermediate state. And you can see whenever we hit a resonance there, we get some photon scattering and momentum is transferred. So we have to make sure that we're always well away from these resonances. So these are the promised first results. So what we did here was we used as a diagnostic tool just the time of flight pictures. So the BC was first created inside an optical lattice. We then applied some Rydberg excitation, and we looked as a function of duration of the Rydberg pulse at the phase coherence of the condensate, so how well this pattern here is visible. And we could also extract by radially fitting a thermal distribution the temperature of the sample. So this is just a sequence for different times, 0.5 milliseconds, 0.8, and so on, of application of the Rydberg pulse. And you can see that, well, no big surprise, we lose atoms, we lose coherence, and the temperature also increases. So very obviously something changes when we create the Rydberg atoms. Quite what is happening there, I wouldn't even venture to guess, but I think this is going to give us a lot to do in the immediate future. Just a slight observation here, it seems that when we create, so this is actually, the blue line here is with only the first step laser, so here we don't create any Rydberg atoms, we just scatter photons, and obviously the temperature increases. Funnily enough, when we also apply the second step laser and actually create Rydberg atoms, this increase in temperature is reduced. But this is just an observation without any explanation on my part, and I'm sure we'll have to do a lot of work to understand these features in coming years. Another little aside, which they tested yesterday, just to make sure that the presence of the lattice beams doesn't increase the ionization from the Rydberg states. So these are just Rydberg lines in a Mott, actually, with the lattice beam superimposed onto the Mott. And this is a scan as a function of the frequency of the second step laser. And you can see that the two traces are the same, so we don't, at least on those time scales, create any extra ions or disturb the Rydberg states in any other way. So my time, I guess, is up. So I'll conclude. I guess the main conclusion of my talk is to show you that we have a very high degree of control over matter waves and optical lattices, so we can do virtually anything we like with them. We also now have some control of the Rydberg states, not quite as much, but we're working on it. We've got a whole number of diagnostic tools in place to look at things like phase coherence inside the lattice. We can look at temperature and so on. And obviously the next step would be to implement one of those quantum simulation schemes that we've heard about and just get our parameters right. And this is obviously going to require interaction with the theorists and also experimentalists in the audience. So I'm very glad to be here and maybe get a chance to talk to you. I should also add that I haven't even exhausted the possibilities that we have with the optical lattices, so we can realize, for example, different lattice geometries such as triangular lattices or more complicated geometries, and we'll certainly do so in the near future. But now comes the most important part, to acknowledge our co-workers. So on the lattice part, which has obviously been going on in our group for a long time, most recently we had Hans Lignier, who's now left us. He's in Paris. Yespal Singh, who's now in Hanover, and Carlos Cias and Alessandro Denisini, who were PhD students. Alessandro is now in Innsbruck, and Carlos in Cambridge, UK, not Cambridge, Massachusetts. And but obviously the most important part for this particular application is the Rydberg part, and here we had incredible help from two of Pierre Payet's grad students, Mathieu Vito, who is still with us, who's been with us for a year, and Amundsen Choudia, who did a short stint in our lab. He's now also going to the States, to Boulder. Jagoda Rozagorstovic, who is a PhD student, and Mark Mason, who very recently joined us from Charles Adams' group, who's also tremendous help. My other two co-workers, well, there's Ennio Raimondo, who's head of the group, and Donatella Ciampini, who's a permanent researcher in our lab. And I should also mention Maria Allegrini, who is now starting to collaborate with us on the Rydberg atoms. And I think I've kept my time, and I thank you for your attention.